Okay, thank you. So we've been working on a tool called DIG, domain-specific insight graphs. And so now we have developed this interface that allows you to define projects. And then there are here many projects that people have defined. There's the SEC project, which I'm going to open. I'm going to first do edit. All this information here basically tells the project where to get the data that the crawlers deposited. So we're not going to do that, but basically it has credentials and IP addresses of where all that data is. Then when you open the project, you get several tabs. So the idea, so we have about 3 million pages for this project that the crawlers collected over 1 week. And so you can sample the data set. And so we basically got 200 pages from those 50 websites that I showed you. And then the user can sort of work interactively with this sort of small data set of pages. And so it shows here, so what are all the TLDs? They call them TLDs, top-level domains, even though they are second-level domains. But and then you can sort of get your samples. Then you can run the extractions over and over as you improve them. And then you can, if you press this button, it'll run on the whole data set. So you can install DIG on a server or on your laptop, and then you can work with, say, 10,000 pages. And then when you press that button there, deployment on the full data set, it's running on a cluster. And so DIG is also deployed on a cluster. But the users who were working on this, they were just working on a tiny part of the data set. And then at the end of the day, they left, we pressed that button, and then when they came in the next day, the data set was loaded in Elasticsearch.
So does USC provide access to the cluster, or is this self-deployable cluster?
So we are working on Dockerizing everything. And so by the end of the month, there will be Docker compose script so that you can bring it up yourself with all the services on any machine. It's a deliverable for our project to get all the Dockers delivered by August 25. So it'll be there by August 31st. Anyway, okay, so here's where I control things. Here's where I define the ontology. So these are the fields that they defined. These are the ones I listed before. Let me just pick one, stock ticker. And I'm going to edit it so you can see what you can say. So you give them a name, you give them labels, you can give them colors and icons, so that it looks nice on the screen. And then here are the things that matter. So search importance tells the system how sensitive it is, our searches to this field. So if this field matches, but not everything matches, should it boost the ranking or not? So stock tickers are very important in search. Maybe other fields are less, like address, because address is not extracted properly. Maybe you don't care so much if the address doesn't match, but you don't want to see pages when you search for a stock ticker that don't have that stock ticker. You can say what type it is. The system currently has very few types: strings, dates, emails, locations, phones, usernames. So these are basically predefined classes in our ontology. You can tell it that you want this extraction to be an entity or just text. And so if it's text, it just gets shown on the page. If it's an entity, it's clickable, and then you get a page like this one's. So this is, phone's an entity, and so it tells the system, for this field, the user can click on it, and the system will assemble an entity page for you. So in a sense, you could make everything an entity except things that vary a lot don't make sense to make entities. And then you can say, okay, show it in the facets. So it shows in a facet, show it in the search form. Do I have rules for it? So I'm gonna very quickly show you the rules. So this is a rule editor we built to basically allow people to do NLP style rules in a graphical user interface. So you can think about it as of building regexes. So here's the first rule for extracting stock tickers. So if I click here, then I can see. So basically, I have a lot of tokens. So I can have three types of tokens: words, shapes, punctuations. And so for shape tokens, I can say, it's either a capital character, 2 of them, 3 of them, or 4 of them. And then I can also say that they have some part of speech. I can say whether, I want it to match the capitalization exactly. I can say, length doesn't make sense always for shapes because I already provided the lengths. But I can have a prefix or a suffix. So I say, they have to start with the letter P. They have to end with the letter G or whatever, or several letters. So I get to play around with these tokens, and this is part of the output. So I'm extracting that. And so the idea is, people click on these pluses, they fill in these forms, and you have a sort of NLP-based rule extractor. And so they basically, you type in several rules. So there are a lot of stock ticker forms, but it's fairly easy to see what they do. So this one says, it's the word NYSE, NASDAQ, OTC, QB, followed by a colon, followed by a bunch of letters in uppercase. Followed by a caret, followed by one letter, and then followed by a dot. So, this is all regexes for people who don't know how to write regexes, except they're a little bit on steroids because you can use part of speech tags, capitalization, and so on. And then you can run them. So you basically go here, you type in a bunch of text. It shows you how the system tokenizes that text.
What do you use under the hood for regexes?
So we use a system called Spacey. It's a natural language toolkit written for Python, written in Cython. It's very, very fast, and it has a rule language that supports some of these things. So what we wrote a compiler that takes each of these rules and compiles into a set of Spacey rules. So some of these ones will actually generate 100 spacey rules. So if you have optionals, I mean, they don't support some of the things, like you can only have one length, you can only have one part of speech in spacey rules, so this compiles down to it. And then we modified the tokenizer so that it tokenizes the punctuations, because in these domains, we really want to extract all the punctuations precisely. Otherwise, when it's in English, it'll group like hyphens and so on are not separators and so on. And then you can just run the rules and see what they extract. So it tells you, which rule extracted what. I can just type in the text here and just rerun it, so I can debug all my rules very quickly.
Does this support dictionary usage and matching? So like if you have states.
Yes and no. So I can put a lot of words in here. So you could put 1,000 words in here and it'll work. If you put 200,000 words in here, it doesn't, because it won't even load up on the browser. It works for smallish vocabulary. So like all the states of the union, things like that, it will work. So it's very nice and convenient, because you can just click around and you can enable and disable rules. You can add tokens. So if you want a punctuation token, it gives you all the punctuations and you just match those and so on.
Sorry, I'm joining in the middle. But what is the input text? It looks almost like the output of an AI algorithm, plus some chat comments.
You can put anything you want. So
what is it? It looks like somebody's writing some message plus a news report.
So the way this gets usually, is that people copy paste little pieces from different web pages where they found examples that they want to extract. So, this was copied from different web pages that have examples of stock tickers, and then this was maybe another page. And so sometimes they copied the whole text, sometimes they just you could just type it in and see, will it extract it and so on. So this doesn't have to be coherent. This is just text that you write. I could just erase all that text and actually, if I erase all that text, it will actually be deleted from their application. So I can say, KDD test, APPL, and run the rules, and hopefully, rule 24 extracted APPL here, because there's a rule that says that uppercase letters in parentheses in this domain are stock tickers.
Can the rules be ranked? Or are they hierarchical?
So the question was, can the rules be ranked? Are they hierarchical? The rules cannot be ranked. We have the ability to provide positive rules and negative rules. Negative rules will cancel out extractions of positive rules if they overlap in span. So you could have rules that extract things, and then you say, oh, but I have a bunch of exceptions. So you can define a negative rule for that, and if the span overlaps, it cancels them. So there's like a two-level hierarchy in that sense, yeah. I mean, underneath you can assign confidences, but then we don't have yet anything that reasons with the confidences. Okay, so that's one extractor. The other thing that you can do is you can associate a glossary. So this one also has a glossary associated with it, a glossary of OTC market tickers that the SEC people conveniently have, because they are the SEC people. So they uploaded that dictionary here, and then you can say that you can match that case sensitive because otherwise you get common words, but you can also match case insensitive. So they did this. It took them a couple hours to define the ontology, do the glossaries and so on. And then when you're done, you can actually run this in this other tab here. I won't do it. It'll take about 10 minutes to run on this number of documents. So I'll go and show you this. So this one is the link to the semi-structured extractor, which is called the Inferlink tool, because it's built by a company called Inferlink. I'm going to open one just to make it concrete. So I made a copy, so I did not mess up what these users did. And so what happened here is the system got a bunch of pages from this website called stockreads.com, and it clustered them to identify templates and then created extractors for them. And so this is all completely unsupervised. So I can look at the pages in a cluster. So this cluster contains pages that look like this. And then this other cluster contains pages that look like this. So as you can see, that one website can have sort of different templates of pages. The system automatically tries to identify these templates and cluster the pages accordingly. And then I can open up a cluster, and then it shows me a table with all the data that it extracted from these pages. So what it does is, once it identifies a cluster of pages, then it looks at all the pages and tries to find what pieces of data vary from page to page. And those are the fields that it thinks I want to extract, because that's the information that varies. And then it shows it to me here. But the thing analyzes the structure of the pages. It doesn't understand what those fields mean. It just knows that there's these little pieces of slots in the pages that vary from page to page. And it has some resiliency to sort of be able to deal with some variations in the template. So it doesn't require the templates to be identical. And then it shows me this here. And then it shows me a menu of my ontology. So here I can say, okay, what is this? So the annotation task for the user after they pick a cluster is to tell the system what is the meaning of this information. And so if I look at TSI post higher revenues, what's the meaning of that? So I can look at the page and I see that here. So that looks like a title. So then I go here and I say, okay, that's a title. Now here's a date, but these users actually define multiple dates. So I can go to the page and look for Friday. So it's not there, so this is interesting because sometimes the information is inside part of the tag that is not here, but I can see it here. It's, this is April 17, which is April 17. So I'm going to say this is some kind of the publication date, date of post. And here's it is again. Now, very often the information gets, put on a page multiple times. The system doesn't, the extraction system doesn't know that this is the same information. And so as a user, I decide, okay, I already picked a date of post. I'm just going to delete this one. It's not relevant. Wall Street newscast. So what is that? So if I was them, I would know. So this is the promoter name. This is all the juicy piece of information from this website for them. And so you would say, okay, this is the promoter name. And I keep going, TWSI, that I'm not going to spend all the time to verify. I'm going to say that is the stock ticker. WS newscast, it seems like it's the same thing, maybe abbreviated in some way, so I'm going to delete it. Now this field, it looks like the system is not able to extract it very accurately, and so I'm just going to delete it. And so, so it takes 5 minutes, 10 minutes to go through a complete website and create a wrapper that extracts all the information that is useful from that website. And so, I mean, they did this, they spent about 2 hours, they did about 23 websites, which is what they did use to build this system. And so, you know, the tool is really cool. When it works great. And when it doesn't, well, it doesn't. So, but it works great many times. And so you can basically very rapidly construct a very useful wrapper for your website. And so then you can go and review a different cluster, because maybe this website has different kinds of pages, like cluster 3 is different. So I can now define a wrapper for cluster 3. And then when I'm done, I just publish them. So I go here, and then after I did the verify step, so in this cluster, it extracts maybe, you know, slightly different information. And then I go and I say deliver, and then you can publish. You can also get the rules, and because we're in a computer science venue, I will show the rules so that you get some insight into what is going on under the hood. So what the system does is infer regexes that delimit the start and the end of each field that varies in a page. So it'll sort of templatize the page, look at what varies, and then construct a regex for everything that varies. You have this little thing that varies. It figures out a regex on the left and a regex on the right that uniquely characterizes that spot of the page across all the training examples. And so, you know, so for every little piece, it has this, you know, and it tries to do the shortest regex. It builds the regex from character engrams, from 6, 5, 3, 6 to 2 character engrams. And so this are the sort of shortest ones that it can find to sort of characterize these places, and then you know, it has some stars when, you know, it does some hierarchical reasoning to find these things. So the regexes look complicated, but they are sort of completely automatically generated. And then the only thing, when I curated the rules in that interface, I'm changing the name to be the name of the property that you know, I chose in the menu. And then the system just runs these rules by applying these regexes and pulling out the pieces of information. Any questions about that? So this system is available open source. So if you're interested, you can download it. So,
I'm sorry, going back to the clustering, is the clustering algorithm working off the content of the pages, the
structure or a combination of both?
Okay, so is the clustering based on content, on HTML structure? The clustering is based on the visible content of the page. So what it does is first extracts all the visible strings from the, by using basically beautiful soup. And then it's clustering the pages based on common visible strings. And it has sort of a greedy algorithm to compute those clusters. Yeah, that's, that's how they did it.
Well, it was interesting because it looked like the clusters seemed to be together by format. So that's why I wondered if maybe there was some kind of something on the HTML hierarchy or whatever.
Yeah, it turns out that when the visible words match, the format also matches. Yeah. And then when you're sort of done, so they did. Oh, I got lost. You can also download the data in CSV, in JSON, and so on. So here you can see all the data sets that they published, that are published, are the ones that got done. And so, these are two SEC investigator folks defined extractors for 23 different websites, which, it's pretty nice. And then they just ran it, and this is the GUI I showed you is what they got. So after they worked 6 hours, that's what they had. So this is what they got from their 6 hours of work with the tools. We will make, the slides have pointers to these tools, and everything will be available as a, MIT, it's MIT licensed, so you can use it for commercial purposes if you want, and it'll be available in sort of Docker Hub, so it'll work on Linux and Mac. Sorry, Windows most likely won't work. Any questions? It's your turn. I have slides that have additional details on the extractors, but we won't, so you can sort of see where you can sort of find them and alternative tools. And so we'll go here.
Okay. Hi, everyone. I'm Mayank. And I'm going to be taking over on the knowledge graph completion section. And also, if we have time, so this one, right? And if we have time, then on search. So, everything we saw in the GUI right now, we're doing information extraction, and, as we saw, it can be noisy despite, all our best efforts to try and do good extraction, to define wrappers, but there's still noise. And, I think Pedro mentioned briefly earlier that, when we have high recall extractions, we can use that in a very judicious way to sort of bubble the ranking up and get relevant pages to the user when they're searching for, stock tickers or, whatever their needs are. So I'll go into that a little later, but right now I want to get to the, the very real problem of what can we do about the knowledge graph, which is noisy. So, the extractions that we have, the kind of noise that these extractions contain is actually not random if you think about it. So, just some examples. So, for example, the postal code could very well get extracted as a phone. So why would that happen? Because, the phone is sort of like a regular expression. And then the postal code, here in the US, it's sort of 5 digits, but, it can be 5 digits and then hyphen 4 digits. In some other countries, it can look a lot like a phone number in the US. And so, there's always this tension because you can try to extract phone numbers, trying to get high recall phone numbers because they're so important, but then you'll also end up getting some postal codes as phone numbers if you try to get high recall. And, other examples, email address or social network ID can actually get interchanged, if you write them a certain way. The third problem, which is sort of much more widely studied in NLP and was briefly mentioned, is this entity disambiguation, which is, the example we like to use is Charlotte, North Carolina, the location versus Charlotte, the person. So the main idea is, how can we detect the links which are really wrong? So, somehow this is after the extraction has taken place. So everything that we're going to cover now is, so we had sort of this stepwise approach where we had the crawling, the domain discovery, then we did the extractions, we stored the knowledge graph, and so this stuff comes after that. So we've extracted what we needed to extract, and so now we're really trying to repair some of what we've extracted after we've done that. So the main idea is how do we infer which links are wrong? So if by accident we got Charlotte, the person, as Charlotte, the place, can we use the other extractions and the context, the words, and so on to figure out that this is wrong, and so remove the link so that we're not making the search any noisier than it needs to be, and also try and predict new links. So if we can, so a very simple example is geotagging. So if we figure out that Charlotte is with very high probability is Charlotte, North Carolina, we can sort of add information and predict links, that the state is North Carolina, the country is the US, those are sort of more explicit. We would use the geonames knowledge base for something like that. I mean, the system a priori does not know that Charlotte is in North Carolina and North Carolina is in the US, so we would have to use an external knowledge base. If we, for the stock tickers, for other things, if we can get new links, if we can link the stock ticker to the name of the company, that might not, it may be that in one page you extracted the stock ticker, in the other page you extracted the company, maybe in a third page you extracted the stock ticker and the company. And so, these links are sort of implicit. There is a indirect link between them. And so you can try and infer that, this stock ticker and this company, with very high probability are referring to the same thing. And, even like improve your extractions a lot more by adding information to the graph. So knowledge graph completion is sort of very popular here at KDD and in various data mining conferences, has been studied for a long time, both in usual domains, not so much in unusual domains. So three of the most popular and sort of most enduring and also the hot topics today are sort of, entity resolution, which is sort of the oldest of the three and in some sense the best studied. So it has a lot of, it's been studied in many different communities. So for those of you from databases, there's the record linkage problem. It goes by that name. From NLP, it's entity linking. It's sort of very similar to entity resolution in a sense. More recently, there's the probabilistic soft logic, which is, statistical relational learning framework. So, this has been popular throughout the 2000s and even now is seeing a lot of work. And then the third one, which is the most recent, has really taken off in the last 5 to 6 years, including several papers at KDD, even this year, is really knowledge graphs, embedding knowledge graphs, just like we embed words in documents and sentences, so embedding knowledge graphs into vector spaces and then trying to do some kind of inference in the vector space. So I'll go into more detail on the very first one and then a little less detail on the next two, but we'll have time for discussion, so we can always go more, and I provide some links and other things in these slides as well. So let's move on to entity resolution. So the definition of the entity resolution problem is quite simple, even though the problem itself turns out to be hard. So the problem is that, how do we cluster mentions that refer to the same underlying entity? So the text over here is very small, and so that's a little bit of an deliberate irony, because the entity resolution research literature itself suffers from an entity resolution problem. So if you try to do a literature search, if you just search for entity resolution, you're not going to find all the relevant literature. You have to search for all of those terms actually over there, which are in very small text. So it's record linkage, duplicate detection, reference matching, entity clustering, approximate match, fuzzy match, reference reconciliation. So it's a little bit of an irony that, the very problem that we're trying to solve has itself cropped up in the among researchers, which sort of, is not surprising because it crops up in every community. So it's there in social media, it's there in every community. So it's really a ubiquitous problem in several communities. So I'll take a sort of generic example. So we mentioned Dbpedia earlier, and the graph on the left-hand side is Freebase. So Freebase, for those of you who are familiar with it, used to be sort of an open knowledge base. Then it got bought. The company that owns Freebase got bought out by Google and sort of folded into the Google Knowledge Graph. So Freebase is actually a very big part of the Google Knowledge Graph, and but it's not updated anymore. So it's sort of in a frozen state. If you can still download it, it's in a frozen state, and has been since I think more than a year now. And Dbpedia, of course, is derived from Wikipedia, so it's it keeps getting updated every year, and I think even more often than that. And it's derived from the info boxes in Wikipedia. So, we can see, even in, simple things, companies, people, we see this problem across knowledge bases. So we have Microsoft Corp in Dbpedia, but we have Microsoft in Freebase, and we have Paul G. Allen in Freebase, and then Paul Allen in Dbpedia. And there are actually multiple Paul Allen, so it's not really as simple as string matching. Looking at this, you might think that string matching might work. As it turns out, it's not enough because you have many Paul Allens, and you quickly run into ambiguity problems. So you have to use not just the string features, but also context and other things to try and really infer which things refer to the same underlying entity. And in unusual domains, this is even harder because we don't fully understand what even constitutes an entity. So, it could be, with the SEC, I mean, you can try to link, for example, the stock ticker symbols, but a harder entity resolution problem is, figuring out, for example, the promotion company that is behind several stock ticker symbols. You're not going to directly observe the promotional company. It's sort of like a latent entity. So in unusual domains, we have many latent entities, which are sort of like these clusters. And so we're trying to link clusters of things to each other, rather than just, nodes to each other. So it gets, like one level harder in that sense. But already this problem is very hard. So just, finding out which nodes link to the same node is already not a solved problem. It's kind of like IE. We've seen a lot of improvement, but it's not considered a solved problem. And the other thing to be wary of with any knowledge graph, usual or unusual, is unlike tables, in databases where each row, sort of refers to a single type. Like usually the table is limited to one type of thing. Like you might have a table of people, or you might have a table describing companies. In the knowledge graph, you have entities of multiple types that are sort of linked to each other. So it's this very rich, interconnected kind of data structure. You have companies, people, and so on, which are sort of all linked to each other. And so it's each type sort of has its own characteristics. So if it's a name, for example, then, if it's a name type, if it's a person, then we know that SSN, would be like a strong feature, right? So you would want, if the SSN is available and it's an exact match, you would sort of want to weight that higher. If it's a company, it's not even going to have an SSN. So, it's very heterogeneous. Once you start looking at different types, you have to think about different features, and, you have to usually train different classifiers for each type. So, it quickly gets very heterogeneous. And so that's yet another problem. So how do we do it? So it's an old problem. So there have been, lots of techniques have been proposed over 50 years, actually. And the ones that sort of dominate now, like in so many other problems, is really some form of machine learning. So I've listed 3 surveys, which sort of cover the problem from a slightly different perspective. So the third one, the one by Christopher, is sort of it's a synthesis lecture series. So if you're sort of really interested in learning a lot more about entity resolution, I'd recommend the book. But the other 2, so the one by Kyopke and Ram is really an evaluation. So if you're familiar with the area, you're familiar with many of the techniques, and you really want to see how they do on different data sets, that's the one. 2007 is sort of it's a traditional survey-like paper. So there are two kinds of methods which are turn out to be very important in unusual domains. So the one on the right-hand side, unsupervised, is obviously the one that we hope we can use, but it turns out that it's much easier said than done. The quality is not good compared to the supervised methods. But compromise is semi-supervised learning. So given just a few training samples, can we somehow train a system where we're able to use the unlabeled data as well as the few samples that we have labeled, the few pairs of nodes that we know refer to the same thing, and try to get something viable. Also, the other technique which is really popular is this collective representation. So I'll give an example very shortly, but the idea is that this is relational learning. So when you sort of have, let me just take an example. When you have a domain like this, for example, co-authorship. So this is a very popular example for this. The idea is that if you look at these 4 papers that were published, they have this dependency. Like the authors tend to collaborate with each other more frequently. That it's not random, right? If author A collaborates with author B on some paper, chances are high that they're also going to collaborate on some other paper. So if you see, papers where you see sort of like, Jeffrey Ullman and then Jeffrey D. Ullman, and then in the third one, it's sort of J.D. Ullman, and then you have A.V., and then Johnson and so on. If you can sort of, propagate the information that, if I link an author in paper 1 and paper 2, and I link an author in paper 2 and paper 3, and, I do that for several authors, and these authors are co-occurring, then, I can use that in some way to do this collective graph propagation. And so for details, I would refer to the Bhattacharya and Gittur paper, which sort of models this as a generative model. So it's sort of like LDA. They propose an LDA model for, modeling these kinds of dependencies and sort of, doing collective reasoning and giving you the links over the graph. So I will say, though, that one of the problems with such approaches is that they tend to be expensive. So, it's collective reasoning, so it's going to be a little expensive. And the other thing is that it does require you to have some domain knowledge. So this is where domain experts come in. So, for example, in the co-authorship domain, we sort of have the assumption that when we see 2 papers with authors that look similar, there's a high chance that you're sort of looking at a collaboration, a repeated collaboration. So the assumption is that authors, tend to have repeated collaborations. In the same way, in the human trafficking domain or in the SEC domain, we can make similar assumptions. So in the SEC domain, one assumption would be that, like the promotional companies tend to use a certain kind of templated language. So when they're trying to promote the stock, they don't rewrite, the promotion from scratch. So it may be that, that is, if you can sort of, develop a language model, then, the same promotion company will tend to use a similar kind of language, across the different stocks that it's promoting and so on. So, those kinds of, you need to model, in the graph, the collective, what you really want to capture in the collective algorithm. So, the next, sort of thing to think about is that when you see like two entities, you need to extract features from the pair of entities, and then, it's a feature vector that, is going to go into the machine learning, right? So the question is, what features can we use? And, this is, again, something which is useful to know, because there are packages that now implement many of these string similarity functions. So the character-based one, the famous example would be edit distance. So very good for names. So, if you have names and they have, for example, Jeffrey Ullman versus Jeffrey D. Ullman, would have sort of small edit distance, and also some of the others, Q, Gram, Jaro. The character-based ones are really good for names. The token-based ones, the famous example is TF-IDF, obviously, but also Jacquard. Are really good for extractions that have multiple tokens in them. So address, for example, would be a good one. If there are changes, there are some tokens that are different between two addresses, this is something that would be able to capture that. And then the third one, which a lot of people are not familiar with, outside, the census community, I would say, is really the phonetic-based matchers. So if there are two strings which sound the same, so you have Catherine with a C and then Catherine with a K and then a Y in the middle, that kind of thing would be difficult for some of the string similarity measures to catch. But the phonetic ones would actually tell you that, in these two strings sound the same when you sound really similar when you sort of speak them out loud, and there are algorithms for converting the string into a phonetic code, which you can then use, for further comparison. So just some packages down below. So second string, Febrile and Whirl are sort of three popular examples that are open and have a lot of documentation. So, this is something useful to know because, these functions are what you're going to use ultimately to convert your nodes into feature vectors for doing entity resolution. Unfortunately, this sort of works for usual domains. For unusual domains, the problem is that we have to deal with many non-text fields. So, it's the string, token, and phonetic are sort of designed for string. They're string matching functions. But in the unusual domains, we have a lot of things that are not text. So, just some examples that we've seen earlier is, the tracking numbers. So, we're all familiar with the, tracking numbers in UPS, USPS, and so on. When we're comparing tracking numbers, the difference in the number has no meaning. So, if you have a long tracking number with, say, a 5 at the end, and you have the same tracking number but with a 4 at the end, the difference of 1 does not mean anything. It can be, it's a different number, it's a different package altogether. So if you use some normal feature like, that this is a number, so I'll just calculate the difference in the number or some kind of Euclidean distance or something like that, and, it has no meaning, right? So you have to sort of, learn somehow that, we can't use a standard numeric feature for tracking number. We can't use a standard string feature for review ID. If a character changes or the ID changes, even in one character, it's sort of meaningless. It doesn't matter whether two review IDs or two social media IDs are different in one character or several characters. It's a harder problem than just comparing the strings. And of course, the stock tickers for SEC, which is an interesting example because it turns out that for the stock tickers, they don't really follow a clean-cut pattern. So if you have Apple, if you look at the stock ticker, it's sort of AAPL. And if you look at some of the others, then it's the first few letters of the company name. Sometimes it's a synonym, and so on. So it's more irregular than it sort of looks. And so, if I want to know that, this stock ticker and this company name are sort of referring to the same entity, what features can I extract from that pair? When there doesn't seem to be an obvious pattern, comparing the two. So one very neat technique, which, works very well for when you sort of don't know what the underlying string similarity is to try and learn the string similarity function. So this is sort of something that has been explored mainly in the database and sort of early KDD literature, I would say early 2000s, and then sort of slacked off a little bit. But there's a lot of potential here, especially for unusual domains. So the idea is that you have some kind of a model. So this is a famous one, a generative model for modeling edit distance. So you have things like, the D over there that you see is like, when you delete a character. So should the character be deleted, in order to align the two strings? The I is, should I insert a gap or should I insert something? So the idea is that you're trying to model two strings, you're trying to align two strings by modeling the changes that you need to make to one of the strings to align it with the other string. So if you have, for example, suite 1001 and then ste.1001, the way that you would align those two is that you have to delete the U and the I, and then you have to insert the dot, right? So it's sort of a three-step. You need to sort of delete two characters, add one, or maybe you need to add the dot and then delete two characters. There are ways of doing that. But the idea is that you need to do some operations to align the two strings. So that's how edit distance works. It computes the minimum cost of aligning the two strings. but usually you give it the cost matrix. So you tell it that, if I delete a character, it's going to have cost 1. If I insert something, it's going to have cost 1. In this case, we're actually learning the cost, and not just learning the cost for, for the operation, but also which character the operation is working on. So it's kind of like OCR, when you have like 0 and O, you often see in OCR systems, the 0 in a document can get translated as O because the OCR has errors in it. So, that kind of error would have much lower cost, presumably, because it's an OCR error, than say O and P or something like that. That would have higher cost because it's sort of less likely that the two strings are referring to the same thing. So this is this paper by Bilenko and Mooney in 2003, sort of covers this algorithm and has pointers on how to, implement this. It's a supervised algorithm. You give it pairs of equivalent string pairs. It learns the parameters, and then you can apply this model to new pairs of strings, and it gives you a score, on how similar the two strings are. So it's really a very nice, adaptive string similarity that sort of, takes the burden from you of trying to pick, which string similarity should I use, what do I do, so, this is a useful trick to know for unusual domains. And the next problem is really an efficiency problem. So, if you sort of think about this, we're trying to infer links. So we have to extract features for each pair of nodes. So if we have, a node, like this is sort of an abstract diagram where the same colors refer to the same entity. But, if we do this for every pair of nodes, like we can do this for every pair of nodes and then get sort of a link probability or a feature vector for the link, and then, do some kind of reasoning or machine learning, which is expensive. If we do this naively, it's going to be quadratic because we're doing this for every pair of nodes in the graph. So that's O of mod V square. Whereas the number of link mentions that you kind of see here are just 2. So even in this small graph, we see that, you have, 4, 5, 6, 7, 8, it's sort of 9, 3, 4, 5, 6, 7, no, 10. So 10 nodes, which, pairwise would be 10 into 9 divided by 2, right? So that's 45. Whereas the number of positives is only 2. So there's enormous class Q. The number of positives usually in the entity resolution problem is much smaller than the number of negatives. So you do many wasted computations if you sort of do this O of mod V square. And for millions of entities, I mean, it's simply not feasible to do, like million square computations, even in distributed setting. So how do we make this more efficient? And for this, there's a trick called blocking, which is widely used in the ER community and carries over to the link prediction community also, where you sort of learn this function called a blocking key. And so the idea is that the blocking key is like a configurable inverted index function. So an inverted index would be something like tokens last name. So that means that in this case, you tokenize the last name attribute of the node. So let's imagine these nodes are all people. So we tokenize the last name, and then, if two nodes sort of share a token in the last name, only then do we compare them. So it's kind of like this pre-processing step, and you can sort of see that they're overlapping. So, presumably, this is like one token in the last name. This is one token in the last name. So this node, these two nodes, sort of share, two distinct tokens in the last name, maybe because they have like sort of one of those last names with hyphens in them or something like that. And since we do that, we can sort of we generate a candidate set where we apply, the similarity function, the expensive classifier, the collective method, whatever it is, only on the candidate set. So in this case, we've reduced, because we only have 7 unique pairs, such that two nodes, both nodes in the pair fall within the same block, we've sort of gone from 45 to 7. So there's already a very high reduction in complexity, by doing that. For big graphs, it can be as high as 99%, 99.9% even. Theoretically, it is still quadratic, but in practice, you're going from million square to approximately a million or, a constant times a million, usually. So, a good blocking key is really something that achieves high reduction, but you also want to achieve high recall. So by high recall, we mean that this candidate set should be a superset of the positives. So, it's not going to work if you just, generate some candidate set where, the true positives get pruned out somehow. So if you choose like a really bad blocking key, for example, tokenizing on the first name, it could be, that you don't get good reduction, or, there are people who sort of don't mention the first name, or the first name initial is mentioned, but not the full name. It would get pruned out and you would not get good recall. So, usually we want to design a blocking key which has high recall and high reduction. And again, in unusual domains, we want to try and learn a good blocking key. So we don't want to try and guess what's going to make a good blocking key. And we want to give training examples of true positives and true negatives and learn how to do the blocking. So there's some existing work, again, on this. And so the main idea is that we are learning these rules, what we call the disjunctive normal form rules, with indexing functions as atoms. So, these papers sort of take you through, the formalism for sort of learning rules such as, what you see here. So, this would be an example of a learned blocking key, which is, we look at the common character trigrams in the last name, we look at the numbers in the address, we look at the last 4 characters of the SSN and, sort of combine these to have this configurable inverted index function. So in that sense, it's very different from an indexing function, which is, just based on text or, like we see in the IR literature. This is really, it's something that, again, learns the indexing function from some training examples. So this is a very nice technique for, that has been studied in ER, but hasn't been applied as much to, other graph theoretic applications where, you have to do some kind of link prediction or inference. And so, for those of you who are sort of working in a graph inference, side of things where you're really trying to do inference on large-scale graphs, this could really be something that you could use, to cut down on your complexity. So putting it together, the way that entity resolution is done today is really that you have your graph inputs, you have some training set, which is links in the graph. So you have some links of which nodes refer to the same thing, and you also have some negative links, which is that, these two things don't refer to the same thing. And you use this training set for, learning your blocking key, learning your similarity function, assuming that you're using some semi-supervised or supervised method. And, you first do blocking, you generate your candidate set. So now you get a much more sparse graph. The edges is not O of mod V square. It's smaller than that. It's approximately, sort of superlinear in O of mod V. And so on the sparse graph, you can then apply, whatever technique you want, which could be the graph propagation, it could be pairwise classification of links. And then finally, you get your resolved entities at the end of it. So, that was sort of a very quick overview of how to do ER. So I didn't go too much into the, into the actual algorithms. But if you're sort of interested, there are a number of packages sort of designed for different things. One of the problems is that they still tend to be very domain specific or a little bit inefficient. So, Febrile, for example, was sort of designed for biomedical record linkage. They wanted to get very good performance on biomedical data sets. So they kind of designed it for that. Dedupe, which is if you have small graphs, it's written in Python and you can sort of, use that for smaller graphs. For bigger graphs, it doesn't have very sophisticated blocking. So unfortunately, it tends to crash very quickly once the graphs become big. And then the last two, Limes and Silk, are designed for the semantic web. So they're on RDF data. And some recent work has tried to learn the similarity function. Traditionally, they required you to say, what makes two things the same. And they sort of just execute it like a rule on the whole graph. So there's still a lot of work to be done in this, for, like sort of these rich, noisy graphs for, data with multiple types. How can we do this without crafting features, without doing a lot of the manual work that is required now? We have to specify and, what string functions to use, what blocking keys to use. So there's really a lot of opportunity to build, systems and sort of come up with approaches that, again, sort of can be done by someone without a lot of programming effort, or can be done on unusual domains. So, this is a research opportunity, I think. Okay, so, sort of leading on from that, we've seen that, domain knowledge is important, so the phones and emails, they're sort of important in human trafficking. Names can be unreliable, the escorts and the human trafficking victims, they often obfuscate the names. They don't want to tell you the name in case you're able to link it to something else. So they have these pseudo names, in a sense, or they go by a different name in the ad. But the phones are very important because that's how you get in touch with them, right? So even though they're obfuscated, if we extract phones, and we do extract phones, as we showed earlier, those are sort of very important attributes. They're like identifiers almost. We've seen that, in SEC, I mean, the phones really were not all that special. I mean, these companies tend to go use like local shell companies, or, the phones are just sort of locally registered already. So there's nothing suspicious as such. But what's really important is, the names, if there are any, could be important because you could link them across different promotions. The promotion companies could be important. The text can be important. So the other example is, the promotional text, and the language model is important. So, how do we use the domain knowledge that we have? So I'm a domain expert, or I'm a computer scientist. I have some intuitions about the domain. How do I sort of use that in knowledge graph completion? So, one way is to sort of define rules, right? So we saw some examples earlier for information extraction. We can try and define rules maybe by looking at a few examples. The problem is that they're too brittle, so they have to be combined with other things. So in extraction, we combine them with glossaries, we combine them with infolink, we combine them with other things, and we can get something viable. By themselves, they tend to be too brittle. If we use machine learning, the problem is that this doesn't look like a machine learning problem. There's no classification here. I have some domain knowledge that I want to use in some way to clean up my graph. It's not really, I don't have any training data. I just know certain things about the domain. So, one sort of framework that has really emerged, as a very powerful way of doing this is statistical relational learning, especially probabilistic soft logic. So the goal behind SRL, for a long time, so the idea was, that logic, has its advantages. Logic helps you to define rules, to codify the domain, to do reasoning of a certain kind. But, logic by itself can be very brittle, right? There are too many exceptions. We really don't know everything about the domain. There are going to be exceptions. There are going to be things we don't know about the domain. So logic by itself is sort of fell out of favor, for problems that are messy and noisy. And, then there's the probability, which is really the machine learning, extract features, or do some kind of inference, do some kind of prediction, and that, of course, relies on extracting features and on training a classifier. It doesn't capture sort of, domain knowledge or dependencies in the way that logic can. So SRL was sort of this movement, still ongoing movement, to try and capture both, to try and get the best of both worlds. And the one that we are going to be covering is very briefly is PSL, which is the very last one. And the reason why PSL, I'll have a slide on that soon, but I want to provide some intuition. So this is a slide where we're sort of trying to do voter opinion modeling. So, this is, I would say it's a usual domain, although the data is a little hard to come by in this domain, but it's sort of classic almost, data mining problem that, how do we do opinion modeling? There are these people who are linked to each other through relationships. You have, someone is a friend of someone is a spouse of someone. So you have this network, the social network of, who's a friend, who's a colleague, who's a spouse. And you're trying to figure out, based on labels for some of the nodes in the graph. So maybe I know that, person A is conservative, person B is liberal. Can I use that to model, whether person C, who's related to person A or B, are they conservative, are they liberal? And we love this example because it sort of captures intuition very cleanly. So it's, what the first rule is saying is that if A votes for P and B is a friend of A, then B is going to vote for P. And we're giving this rule 0.3. So the higher the weight, the more important the rule is. So I'm saying that, okay, with weight 0.3, what I'm saying is that, if two people are friends, then simply using what I know about the world, which is that, two friends, if they stay friends for long, tend to have the same kind of affiliation politically. And so, it's very likely that if I know that A is going to vote for P, chances are that B is also going to vote for P, assuming they're friends. But then the interesting thing is you go on to the next rule, and what that says is that if A votes for P and B is a spouse of A, then B votes for P, and that one I'm going to give a much higher weight. So I'm saying that, if you're married and, you're sort of, it's much more likely than if you were simply a friend. So, if you're like spouses versus friends, then I'm just going to say that, I'm going to give that a higher weight. So it's could be wrong, so that's something to be careful about. So these intuitions could be wrong, could be stereotypes. There are lots of instances when so-called domain knowledge, is brought seriously under, scrutiny. But, it's kind of nice because, these are the kinds of rules that, if I just give you a few examples and I sort of train you a little bit, even if you don't know a lot of computer science, you can actually, or you don't know a lot about this, how to do this technically, you can still write down the rules. And it turns out that there's a really nice package for which I'll give the link. So this framework, PSL, has been developed by Lisa Gittu's group. And she maintains a very active repository. She has open source code, she has tutorials, videos, all of that. So it's very easy. Like all you have to do is sort of, write the rules in sort of a text file, and then you can just run the rules on your data, and it sort of gives you these inferences. And this can be used for very powerful modeling because it's sort of giving you assignments to these atoms. So it's going to tell you, okay, the fact that B votes for P, what is the probability, of that? What's the assignment and what's the most probable explanation? It will give you the most probable assignment of these atoms. So that's kind of you can build very complex sets of rules for a domain if you wish, and or you can make it really simple. But these are some of the advantages of using this. So first of all, it sort of combines logic and inference in a very nice way, just like many other SRL frameworks. But it's very efficient. So if you sort of read the paper on PSL, it turns out that the optimization that they do is it's sort of convex. So they can really, it's convex optimization, so they can do it very quickly, and they can handle large sets of rules on relatively big data sets. And also it's being continuously maintained, and if you run into problems, then they sort of are very responsive also. It's a very nice package that is, kind of nice for expressing intuitions about the domain. And so this is kind of the link. And all these slides are all available on the tutorial website. So, if you go to that link, then you'll see an entire portal for PSL. So, you'll see the video, you'll see a lot of different things about PSL and how to use PSL. Okay, so, it's sort of, two problems, which very briefly I'll go into. So the first problem is that, I know the rules, so I kind of feel like, okay, the rules are something I know, but I really don't know what weights to give to the rules. So it could be that, maybe, spouses don't have the same political affiliation. Maybe it's just it's a stereotype or something we've seen in the movies, but in the actual data, it's possible that, it's very slightly above random. Maybe it's 10% higher than random, that two spouses would have the same affiliation politically and so on. So ideally, I want to try and learn the votes, learn the weights for these kinds of rules. And it's possible to do that in PSL. So in PSL, you can specify the weights, and then you would give the system some training data. And then from the training data, it would be able to figure out, how much weight you should give to a certain rule to sort of fit to the training data. So, that's kind of a nice thing. There's also some recent work on trying to learn rules. So for those of you who are familiar with the literature on this, it's like learning graphical models. So it's the same community and the same set of techniques for trying to learn graphical models. And, the problem, of course, is that when you try to do this kind of learning, the very thing that makes PSL advantageous, which is that these rules are sort of interpretable. There's something that humans can understand and humans can sort of write down and change and play with. If you try to learn the rules directly, you're going to get some very complicated, non-intuitive rules. Excuse me. Some very complicated, non-intuitive rules, which will really not make a lot of sense. So, the logic part of PSL will lose its advantage. So there's still a lot of work to be done in the second area, but the first one is included in the package already, and is quite nice for sort of just specifying the things that you feel are important in the domain and then letting the system figure out how to weight those. And I'll just provide a case study for unusual domains. So we use PSL along with some other techniques for the problem of toponym resolution. So toponym resolution is that, we have an extracted location. So say we have London, in this sentence. And, as people who have worked in the geolocation field will tell you, London, I mean, there are just many Londons in the world. And, this is the one that I wanted to use. It's right next to Toronto, I think, for anyone who's from Canada. But, there's a London here. There are, lots of cities that we think that there's only one city with that name, but actually there's more than one city with that name. And so, you don't want to assume that when you extract London, it's just from UK, or when you extract Los Angeles, it's only from California, because there is a Los Angeles in Texas, there is a Paris in Texas. So you want to be careful, with that. And so the problem of toponym resolution is, when I extract something like that, how can I link it to the canonical entry? So it's a very specific entity linking problem that, when I get this entry, which London is it? There's a canonical entry for each London or each geolocation in geonames. And so you want to try and link it to the right one. And you can kind of see how PSL would apply here, because, when we have the city and we've also extracted a country, we've extracted a state, then we can have very simple rules where we sort of say that, okay, a city can only be in one state and one country. A city must actually exist in a state and country. So if we have, say, Hong Kong, we extract Hong Kong and say there's no Hong Kong here in the US, even in a state or somewhere else. If there's no Hong Kong in the US, then, I don't need to even consider the literal that, Hong Kong is in some state, say Texas, and, it's in the US, because there's no entry for that. So, the PSL would sort of use those constraints to figure out that, would only assign non-zero probabilities to the Hong Kongs that actually exist, and would assign higher probabilities based on what else you've extracted. So if you've extracted like Hong Kong, Asia, then the Hong Kong in Asia will get high probability. If you have like London, Ontario, Canada, I mean, normally, maybe a priori, the London in UK is more probable because it has higher population, which, or higher significance, which maybe you can weight in your rules. But then, when you see Ontario and Canada, then some of the rules that, this state got extracted, a city got extracted, and this city is actually in the state, those kinds of rules, the PSL will then sort of weight the London and Ontario higher. And that may end up being your winning, the most probable assignment. So we found that it actually works quite well for these kinds of things. And even very simple rules can be used to really boost performance in some of the domains. Okay, so we have, just about 10 minutes, I think, before we want to close for questions. So I'm going to go very briefly over knowledge graphs in latent space. So this is still very much an active area of research. So we're starting to see papers even now. And so, this is a field that is sort of, there are new algorithms coming out every year, even now. So I'm just going to sort of give you the basic intuition behind this. And point you to some papers. So the idea is, again, exploiting the low-dimensional vector space. So we've seen this for word2vec, obviously, that's the one that sort of has become famous. A lot of people have heard of word2vec. It's, the idea is that, the words are embedded in this low-dimensional vector space. So in this case, it's only two-dimensional. And, you have these very nice semantics that are captured by these spaces. So for example, if you look in the corner, so that's the famous example, that if you do the operation, if you take the vector for king, and then you subtract man, the vector for man, and then you add the vector for woman, and then you try to check, which word is closest to that, you get queen, which is kind of neat, because it's this totally unsupervised, statistical framework that is really capturing something which seems, word analogy, which is very human semantics in some sense. And so now this has this kind of thing. So not this exact algorithm, but this kind of technology, this embedding technology has become very rapidly popular. So everyone is using it for embedding documents, sentences, graphs, nodes, links, you name it. So the one, of course, that we are concerned with is knowledge graphs. So how do we embed knowledge graphs into the vector space? And the way that it's done is that, the entities are sort of like the words. So each entity is sort of given assigned a vector. The relations, which are the labels, the properties on the edges, could either be vectors or matrices, depending on which method you're using. So the main idea, if you look on the left-hand side, the trans E is actually a classic method now, was published a few years ago. The idea is if you get a triple HRT, so head entity, relation, tail entity, subject, property, object, you want to try and embed the vectors, embed the nodes in the graph and the relations in such a way that the head plus the relation is very close to the tail. So, let's say that, for example, like say I'm born in city A, then, like my name plus the vector, so the vector for my name and then the vector for the city, should hopefully, vector for, I'm born in should be very close to the vector for, the city I was born in. And so we want to try and do this so that, everything is embedded so that when we add the relation to the left-hand side, the left-hand side entity, we get the right-hand side entity as a result. And so, we can sort of do this kind of reasoning over the graph. The second one, which I'm not going to go into, is really they try to model the relations in more complex ways. And this is just a snapshot of, all the work that has been happening. So you can see that, the earliest papers sort of start quite recently, 2011, and Trans H, I think, was published in 2014, and, there's continued to be more work since then as well. And they all sort of use different objective functions. So the very first one, trans E, is trying to minimize the distance, the L, 1 or 2 distance, depends on which one you choose as a parameter, is, the head plus R minus T, which means that the vector for the head plus the vector for relation minus the vector for the tail entity are, the distance is minimized for that. As you sort of keep going down, you see that, it can get complex very rapidly. Some of the objective functions are sort of, quite complex. But the idea is that, it's ultimately you're trying to minimize a sort of an energy function or a loss function so that your knowledge graph embeddings make sense in the vector space. You can do all kinds of reasoning in the vector space. Again, there's a huge opportunity here because when we look at the data sets that all of these papers are evaluated on, I've only seen 2 examples in all of the papers. So it's usually either WordNet or it's Freebase. So the WordNet and Freebase are not unusual in any sense, and if you look at the Freebase, they don't use the whole Freebase, with the millions of entities. They usually use a small subset with, not that many relations really, and even the graph itself is really not that big. If you look at the training, validation, and test, and you sort of add it up, it doesn't even usually add to like 1 million. And if you also see, they have to use a lot of training data for many of the tasks. So it's close to 500,000 triples that have to be used to, train the embeddings and sort of get the links. And the test data is very small. So in unusual domains, you're going to see a lot of noisy links. So it's not clear, how you can get 500,000 links that are guaranteed to be clean. And the number of entities is obviously not 15,000 or something like that. It's millions. So there's still a lot of opportunity to try and use these techniques for a number of applications in unusual domains. So I'm going to skip the applications, except this one. So this is an interesting one. So the triples classification is that you train a classifier. You want to train a classifier such that if I give you a link in the knowledge graph, I give you a triple in the knowledge graph, is that true or not? So, if, for example, maybe I did a wrong extraction, and that would be a triple. So, I extracted, say, a stock ticker symbol. I want to know, this is something that would be able to sort of tell me that, what is the probability of that extraction. And if it's below a certain probability, then, it's wrong. So you can kind of see that, on the FB13, the Freebase 13 and the Freebase 15K, two subsets of Freebase, this, the latest method sort of achieve, something in the 80s, late 70s. I think the most latest results are in the 80s now, but not in the 90s. So there's still a lot of room for improvement, even in the usual domain, and in the unusual domain, no one has done an evaluation. So no one has really tested these methods on, any unusual domain or any domain outside Freebase and WordNet. So, it's really a nice sort of an open question right now that, if we use these embeddings with all of these complicated objective functions, on data sets which are really not that well studied and may have a lot of noise, how well do they perform? What can we learn about them? And so on. And the code is not sort of, very widely available. There's some of these packages, some of these algorithms which I showed on the chart are implemented in this GitHub package. And they sort of use a Theano TensorFlow backend, so you can use either one if you use this. You can use this for sort of replicating the experiments. So it's one of those packages where, they sort of give you some code for replicating the experiments. If you run the code, then you'll get results on those two data sets. It's not completely clear, how we can adapt this, how do we use this in a more general purpose fashion. So it's still a little bit of an undeveloped software environment, I think, for this. And of course, the research problem is that, if we have a different kind of knowledge graph, the data is sparse, or it's we don't have too many examples for a given link, a given property. There's a lot of noise. It's much bigger. Do these techniques scale? If they don't scale, then can we have algorithms? Can we build algorithms that sort of scale and really do well empirically on these? So a lot of empirical opportunities. I'm going to skip the application 3. So this is something that came out of our group, where we sort of converted the locations, because we used it for toponym resolution. We embedded locations in geonames into a vector space, and this is available. So both the embeddings as well as the code are both available online. So if you're interested in toponym resolution, or you want to use feature vectors for nodes, geolocation nodes, then this is sort of one resource that you could definitely check out. And, it works fairly well. So we sort of tried this. This is just one example where we gave it 3 places on the map. So we, use the similarity, to sort of get the black node, which is sort of returned by the algorithm. There's no city over there, but if you actually go and sort of zoom into Google Map, there is actually a city there. So, it's able to sort of use this, the queries, which are the red dots, to sort of give you close locations. So the vectors capture spatial proximity is what we found. You can sort of, the feature vectors are embedding the globe, the positions on the globe in a low dimensional vector space. And so in that sense, it's a nice substitute for latitude and longitude features. So, it turns out you cannot directly use latitude and longitude in your feature vectors, because there's a very complex way to calculate the distance between two places based on latitude and longitude. There's a very complex formula in the geospatial sciences. And, like if you have 0 degrees and then you, like minus 180 degrees or something like that, they can turn out to be very close. And because, the Earth is sort of crossing around. And, if you have small differences in latitude, you can be halfway across the globe sometimes, or not even in the same country, and so on. So, this is really a way of sort of, capturing in a low-dimensional vector space, the positions on the Earth, which can be used instead of latitude and longitude for features. So um, I'm going to skip the part on searching knowledge graphs. We've sort of done it through the demo already, where we sort of showed where we can use the form for doing faceted search. So this is when you sort of know what you're searching for. You know that, okay, what I'm searching for is a stock ticker symbol. What I'm searching for is a name. So you can do that for very specific search. But we also support keyword search. So the idea is that you type some keywords, just like document store. And so this is where keeping the text becomes very useful. So if you remember early on, we sort of said that it's useful to keep the text in addition to the structured information. So the text, we can, because of that, one nice sort of advantage is that we can do normal text search using Elasticsearch, which has Lucene at its backend. So it's sort of designed for text search, optimized for text search. And yeah, with that, we're gonna start wrapping up. So you wanna do the wrap up? Or-
I can.
Okay.
Yeah, thanks. So quick summary, basically going back to our agenda we had at the beginning. And so please feel free to ask questions. We have about 10 minutes. So our sort of high-level bit is about unusual domains and the sort of fun it is to work on them, the enormous social impact that they can have, in large part because they are mostly unexplored, and so any progress is a lot of progress, and they're very interesting. We covered knowledge graphs, and part of the idea is that there's really not one definition of knowledge graph that is sort of dogmatic. We sort of covered a range of knowledge graph representations and shown examples of different ways of doing it, and they are all valid and should be sort of tuned to the problem that you're working on. Knowledge graph construction. I think the main thing that I think I want to convey is it's not something that people should be afraid of, and something that, if you want to do data mining, you have to find somebody else to give you clean data. There are lots of tools out there now that let you very quickly create a knowledge graph where you can start doing a lot of very interesting things. And if you're a researcher, these knowledge graphs are also fertile ground for computer science research. Mine covered the knowledge graph completion, where after extraction, we may still have many errors that we can use machine learning techniques to improve the knowledge graph. Some of that is entity resolution. In the unusual domains, the entity resolution problems can be especially hard because you don't have reference sets. So you have to infer the entities from the data while also resolving them. So you have to do sort of clustering and to sort of infer your entities. Then PSL as a good framework to combine logic and statistical methods to encode intuition, but also use machine learning to sort of learn the weights. How much should you trust your intuition based on the data? So methods for taking knowledge graphs and using them in machine learning, so you can embed the nodes and the edges into a vector space so that you can apply machine learning techniques. And then something we didn't cover in great detail are techniques for robustly searching these knowledge graphs that we know are noisy and incomplete. And a big part of the intuition here is never throw away the text. If you do extraction, always keep the text around, very close to the extraction, so that you can use it for training word vectors. You can use it for robust searching. The text is very valuable. And that's the summary. So, if you have any questions, please feel free.
Are the slides available?
Yeah, the slides are posted on the KDD, on our KDD site that is linked from the KDD site. Maybe we should just go here. There was another question. Maybe you can answer that question while I find the slides.
I was just wondering if there is a dynamic component in knowledge graphs.
So, like we can do knowledge graph construction in a streaming fashion. So, for example, for the human trafficking domain, the way that it works is that the index gets. Okay.
Sorry?
So the question was on. So the question was on the dynamic component of knowledge graphs, and I think the main dynamic content is the data itself. So for some of these domains like human trafficking, the data sort of updates, frequently. So we try to, in our index, the one that supports law enforcement, we update the knowledge graph very frequently, and then you can run the construction and so on, incrementally. So many of the algorithms can be run in a streaming fashion. The embeddings that we saw, can also be run in a streaming fashion. So they use, SGD. So when you get new data, you can just, it's possible in theory. No one has tried it on a large scale graph, but, many of the machine learning, they use SGD. So they could potentially be used in an online setting. For us, I think right now we do knowledge graph construction in a streaming fashion for some of our domains, and I think that is the main thing about the dynamic component. And also, I do want to note that Elasticsearch allows you to update the index and very efficiently. So that's another reason you can add nodes and update nodes, with just API calls. So. Yeah, it's not something which has turned out to be a bottleneck so far, for the techniques that we have shown.
Could you provide more details on the semantic search in the knowledge graph?
Okay, so.
You want to go to the slides?
Yeah, this is the diagram that we had. So maybe this one. Okay, so this is kind of the what happened? Oh. Okay, there we go. Okay, so yeah, this sort of captures what we're doing with that. So the idea is that when we get the query, the original query, it may contain things which are sort of noisy in the knowledge graph. So for example, if you have, you're searching for someone with red hair, the right answer may have auburn, not red, or it may have words like crimson or something like that. And so what we do, the way that we do the robust searching is that we reformulate the query into a set of queries. So the conservative query that you see on the left-hand side sort of is very similar to the original query. We do a proper SQL-like execution. The relaxed query sort of turns some of the things into optionals. So we say that, okay, you don't have to match everything exactly. You can have optionals. The more you match, the higher will be your score. And then finally, it gets even more relaxed. So then it becomes a keyword-only query. So if you're searching for a phone number, hair color, and eye color, whatever the facets are, for the keyword only, we just combine them into a set of keywords in the hope that, you get, if you're not getting anything for the others, hopefully you match the keyword. Maybe the extraction got misplaced, it didn't get extracted, but it's in the text. So the idea is that you sort of build these relaxed queries, sort of cascading relaxed queries, and these are weighted. And then this set of weighted queries can actually be combined into a single Elasticsearch query, which is then executed in the server. And then we sort of get this rank list of results. So yeah, it's sort of semantic query reformulation. We call it that. And this is fairly new work where we have a journal article that's going to be coming out very soon. The revised copy is going to be due in about a week. So hopefully in a couple of months, there will be a journal article sort of describing the technical details behind this approach. But this is kind of, it's based on the query, the constraint relaxation and the query relaxation literature in the IR community and the learning to rank literature in the IR community. But it's very different because from either one, because it's sort of these semantic query reformulations. Where
So just to clarify, you're not relaxing the keywords, you're relaxing the query on the graph.
we're relaxing the query, we also relax the keywords. So that's why it gets more complicated. So for example, we use the glossaries. We can use the glossaries to relax the keywords. So we call that entity set expansion, where we for example, if you have the word Japanese, you're searching for someone with ethnicity Japanese, then we have methods where we will relax the query, and then also in the relaxed query, we will include Japanese and also say Asian. But if you match on Asian, that will have like a lower weight. So there's weighting going on inside the query as well as the query itself is weighted. So it's sort of this algebra of reformulation. And so, that's kind of the search system.
Okay, so the hard problem is reformulating, not necessarily searching the KG. Searching KG is straightforward.
It's straightforward because of Elasticsearch. I think the Elasticsearch query language is very powerful and expressive. I think it hasn't been studied theoretically. I know there's interest in that. There is a lot of interest right now in the database community to study these languages that have really come from the community rather than theorists. But the Elasticsearch query language is very powerful, surprisingly powerful, with a very nice algebra and a very nice way of formulating queries and expressing very complex queries. So yeah, I think I'm sure that maybe some of the MongoDB and maybe MongoDB also has something like that. I'm guessing, but the Elasticsearch one was very impressive. You can really express lots of things in that.
Yeah, so this is the GitHub of the software for the semantic query engine. It's called Sandpaper, and it runs in a Docker container. It translates Sparkle queries in a very simple ontology into Elasticsearch queries into our knowledge graph representation. And it has lots of configuration options. So you can configure what kinds of strategies it uses and so on. Other questions? Comments? Advice?
Okay, I guess it's time for lunch.
Past the time. Well, thanks for coming.
Thank you.
Hope that you got something useful. And please, if you don't mind sending us comments by email, we really appreciate it. Always looking for ways to do it better next time. And so if you have any advice, please send it to us. It'd be a lot of fun. Good luck. Thank you.
Thank you.